In the last several lectures, we worked out perturbation theory, and we discussed how to perform calculation using Feynman diagrams and all that. But we also emphasized the fact that perturbation theory has severe limitations because its applicability is not only restricted to physical theories in which the coupling is in some dimensional ratio small, but also to theories in which the correlation function is dominated by just a few vertices. The counterexample was QED, which is a theory where the effective coupling is actually, in some natural units, a small dimensional parameter. However, you can imagine physical problems in which you have a large number of vertices dominating the observables, like many photon exchange from a proton and an electron forming a hydrogen atom. And as a result of this, these particular observables have a non-perturbative behavior or entirely non-perturbative phenomena like the emergence of bound states, even though the coupling of the theory is small. As a matter of fact, basically all of condensed matter physics is QED, and all of chemistry is QED, and the very existence of molecules, which are bound states, reveals the fact that, or atoms themselves, reveals the fact that most of the time QED is non-perturbative. So, with perturbation theory alone, you don't make a long way across theoretical physics. And the applicability of field theory with perturbative calculations is limited to a handful of scattering problems. Probably you can basically do only standard model physics in some part of standard model physics. Well, I'm probably being a little bit too extreme here. There are other perturbation theories that are occasionally used, like chiral perturbation theory is used in nuclear theory. But what I'm trying to say is that besides scattering, perturbation theory by itself doesn't take you a very long way. So the real problem that one needs to face is what to do beyond perturbation theory. So let's talk about non-perturbative approaches. Or techniques in field theory. And whatever I'm going to say now holds for both statistical and quantum field theory, but I will be specifically referring to statistical field theory because that's the sort of paradigm we are considering in this course. With the only exceptions of adding I's here and there, you can translate this into quantum field theory as well. When you consider statistical problems, the applicability of perturbation theory is even more restricted because most of the time you really are not considering perturbative problems, especially in complex systems. Remember, our working definition of complex system is a system where you have a large number of particles interacting at the same time, so that you can never split the problem as a product of problems of single particle or few particle states, which means that there are many particles interacting at the same times. Even if their individual interaction is small, the collective effect of having many particles interacting very heavily very weakly is a very large effect. Stated differently, condensed matter physics is non-perturbative because if the interaction between two electrons comes with a price of, say, 137, the exchange of photons comes with a price of a fine structure constant of 1 over 137. If you have a 137 electron in your system, then of course, even if they exchange one photon each, the overall effect of interaction will be large. It will be of order 1. Right? So I guess this is good enough for motivating the urge of non-perturbative methods. So the first thing I want to discuss today is the most trivial approach to non-perturbative field theory, which is trivial from the logical point of view, but from the point of view of its actual implementation came much later in the development history of field theories, because it required large-scale computing for becoming practical. And this method is called lattice field theory. Now, lattice field theory is not even a technique in statistical field theory. It's just, how will I say, it's just a definition of statistical field theory naturally leads to lattice field theory, while it becomes a techniques in quantum field theory. What do I mean by that? It will become clear in a couple of minutes. So what is lattice field theory? In lattice field theory, it's a way to evaluate correlation functions. For instance, we're interested in a two-point correlation function in our scalar field theory, for instance. Okay, so what do you actually do? You regularize your fields on a lattice. Quite normally, you adopt a square lattice. But you may have rectangular lattices, and so your integral will reduce, as we have now become acquainted to by using this several times. It will become a product of regular Riemann's integrals with one variable associated to each lattice point. So that's k. This is psi k minus negative n a. So let's call it, say, suppose this is a two-dimensional lattice. This will be negative divisor j a. This will be k negative a versor I, and a is the lattice space. So if you do that, then your correlation functions will become phi of x1, and x1 would be a point on the lattice at this point. So maybe it's some kind of n x y z times a, when n is a macro index. In this case, it's a two-dimensional macro index that points one point on the lattice. So it will tell me maybe if this is the origin, n could be like in this very case here, it would be 1, 2, right? Phi of x or 2. And then you will have a discretized version of your Hamiltonian, and you divide the same integral by the partition function. And your discretized version of the Hamiltonian will contain discretized derivatives. For instance, I guess if this was a one-dimensional system, this would be like phi I plus 1 plus phi I minus 1 minus 2 phi of I divided by 2a squared summed over I. And then, of course, this is the discretized version of the Laplacian. Well, let's do this in another slide. So up to now we defined the partition function on the lattice. What I'm missing is now a discretized version of the Hamiltonian. Let's look at the Hamiltonian. Well, I will have a sum over, say, dimension and d equal 1 to d. Let's imagine 2 dimensions, for instance. And then I will have phi. Then I will have a sum over the lattice spacing points, sum over n. N is an index that will run over all lattice points. And I will get phi of n. And let me, rather than use it here, let's use it as pedx here. You can use it as an argument, 5 and A, but this is X, right? And then I will multiply this by phi n plus n d n plus I n d plus phi n minus I n d negative 2 phi of n divided by 2a squared, and then I put a negative here and another 2, because remember in our theory the gradient comes squared. So what this is telling me is if you look at this is nothing but a discretized representation of the operator integral dx phi negative Laplacian to phi. Why? Because the negative Laplacian is actually a sum over d squared by dx squared plus d squared by dy squared of phi. And so you have a sum over two components, x and y. This is the sum of the two components, and d equal 1 is x, and d equal 2 is y. For each of them, I move forward by one step, I move backward by one step, and I subtract the value of the function in the point. That's a discretized version of the second derivative. And I multiply this by the other terms. Yeah. So that's the discretized operator. And then all I'm left with is the other two. So I'm get the sum over the lattice spacing n of phi square of n times m half plus some lambda to the 4 factorial sum over n, and then I will get phi to the 4th of n. So that's my lattice Hamiltonian. And it's a function of many, it's a regular function of many variables. So with this definition, computing partition functions, correlation functions, just you can use standard Metropolis Monte Carlo to generate ensembles of field configurations. Once you have an equilibrated ensemble of field configurations, then you evaluate correlation functions and you use the central limit theorem, and you use it to evaluate correlation functions. So in this respect, I'm saying lattice field theory for a statistical field theory is not even a technique, it's just defining what the partition function of a statistical field theory is. Remember, for us, a partition function of a statistical field theory is a continuum representation of what it really is, a discretized path integral. And the partition function is a physical interpretation of a real partition function. So doing lattice field theory is nothing but then applying what we mean by statistical field theory. It's not even a technique, it's what it is. So I guess one could, if you're a computationally oriented guy, you might even try implement your simple lattice field theory for a two-dimensional system and see what it comes. I would think if I want to assign a project on that and see if this is actually an interesting thing to do for this year. Well, we'll see. But if we look at the problem from a wider perspective, we might consider lattice field theory as a technique to solve quantum field theories as well. Now, this part of the lecture is not in the course, is, if you want, digressions for those of you who are also taking quantum field theory along with statistical field theory. And this is just, say, a Wikipedia-style introduction to lattice field theory for them. And by Wikipedia style, I mean I'm not trying to be exhaustive in any way or to be detailed. Just giving you an idea, since it's a name you actually hear a lot. So let's suppose, for instance, we are dealing with the Klein-Gordon theory. So now the Klein-Gordon theory is defined by a generating functional, as we know. But this time is in 4 dimensions. And I have a complex extreme, a complex exponent of the fields. And the exponent of the field is, again, phi of x, the D'Alembertian phi of x. And then maybe we have a phi to the 4th again. And now the integral is in the Minkowski space. So let me write M to remind myself that this is a Minkowski space. And this is, for instance, a real scalar field, or it could be a complex scalar field, in which case here would be star. Now, the important point here is that you cannot simply compute. Now, what it comes out is in quantum field theory, you're interested in time order correlation functions. And time order correlation functions are written as path integrals. So really, in quantum field theory, you're interested in objects like x1, x2. I'm focusing on the 2-point function for sake of simplicity. And this guy can be written as a path integral in the following way. Now, these are numbers, remember, either real or complex, no longer operators after you do the path integral presentation. Now, the point I want to make is that you are no longer entitled to use Metropolis Monte Carlo, because this is, in fact, not a positive definite real number. Is in general a complex phase, because the action is real valued, but the exponent of the action is a phase. So you cannot simply put this on a Monte Carlo, because you cannot attribute a statistical weight to your distributions of field values on the lattice. So when you want to tackle a non-perturbative field theory problem in quantum field theory rather than in statistical field theory, you have an issue. And the only way you go around with this issue in 2020 is by exploiting one of the tricks we introduced at the beginning of this course, which was the Wick rotation to imaginary time. So basically what you do, you perform an analytic continuation of your partition function and your theory in general from real time to imaginary time, defining what is called Euclidean generating functional, which is basically a same expression. Well, of course, this is a generating functional. You need to have a term like this. It's an extension in which you replace the Klein-Gordon action with this Euclidean version, which I remind you is obtained by transforming tau into negative it. Sorry, t into negative I tau. And after you do that, we've seen this explicitly for the Feynman path integral. Your I will disappear, and we'll basically get an action which contains a sum of potential plus kinetics, which in this case, for pure Klein-Gordon field, we will turn the D'Alembertian into a term like this, where the D'Alembertian is the Euclidean D'Alembertian, which contains sum of space and time derivatives. Now, all of a sudden, either in real or complex Klein-Gordon field, your theory will be definite, positive definite, your action will be positive definite, and the exponent here will be real, leading to a probabilistic interpretation of your theory. So you can still evaluate correlation functions in Euclidean time. And now if you go back on the notes or on the lectures we put online, you will discover that you can still use Euclidean time formulations of path integrals to learn properties about ground states, for instance. And I want to give you an explicit example. Suppose we are interested to know whether two scalar particles interacting with some potential, local potential, form a bound state or not. That's a typical non-perturbative problem, a problem you cannot address in perturbation theory. And once again, I apologize for the people in the audience who are not from field theory. This is not going to be a topic I will ask in the exam. This is something I give to complement your background in field theory. For those of you who are coming from quantum field theory education. But suppose we're interested in computing, suppose we're interested in finding out if two scalar particles, which I denote here as a line, can interact with a local potential and give rise to a bound state. So basically they have a number of interactions like this, and maybe also interaction like this. See, each of these vertices is a phi to the 4 vertex, and correlation functions are dominated by an arbitrary number of diagrams like this. And you cannot simply order this diagram saying I can discard all the sum of over all of these contributions because they are irrelevant. They all somehow count. That's the nightmare of non-perturbative physics. You cannot discard anything. Well, if you do that, so basically the way you want to consider a correlation function in which you create two particles, maybe in the same point, maybe in a different point. It depends on if your theory is supposed to be gauge invariant or not. But these are technical details. Scalar field theory is not a gauge theory. You can create them wherever you want, but you like to have them closed. Let's suppose you created a given distance a. You absorb them after some time, some Euclidean time, at a given distance, say suppose a. So basically what you're looking at is a correlation function in the form, time correlation functions in Euclidean space between the fields at some point x time tau x plus a time tau, or let's say y. And maybe x times 0, y, or even x naught and y naught. They don't necessarily have to be the same positions. Now, if these two particles, now clearly this correlation function will have a spectral representation. We discussed the spectral representation of Feynman propagators earlier in the course, and we discovered that when you go in Euclidean space, you're dominated by the lowest state in the system, right? The ground state wave function. Now, clearly, the states that will contribute to the spectral representation of this propagator will not be the plane ground state, because in the plane ground state we will not have these two particles. And therefore, if it happens that these correlation functions will contain a single ground state after I project out to zero momentum components, that will be a bound state. Because if the two particles are not bound, then you have a continuum of state depending on the relative position of the particles, right? While instead, if the two particles are in a single bound state, then there is a single bound state with zero energy. So in other words, if I integrate over the momenta to the positions in order to have to select out the zero momentum space of this correlation function, and I look at tau going to large, if this correlation function will drop linearly, then I can extract the existence of a bound state, and the slope of this drop-off will be the mass, the energy of the bound state, or the mass of the bound particle. So that's how people on the lattice compute the mass of the proton conceptually. For instance, by setting 3 quarks, absorbing 3 quarks, and letting the system evolve in imaginary time, and computing Monte Carlo. Now, there are technicalities when you involve fermions, and I will not go into that because that will generate a course on field theory. All I'm trying to say in this lecture is that you can use the trick of going to imaginary time to learn non-perturbative features of quantum field theory. The issue, though, is that you are not having access to all possible observables you would like to have, but only to some modest and limited information, for instance, ground state, bound states, and stuff like this. So there's a whole plethora of observables that are inaccessible to quantum field theory, even with infinite computer power, because there's simply no technique that enables you to compute that. Now, that's one of the challenges of quantum field theory, that for some times was an exciting feature. Many people were trying to invent non-perturbative methods, but I think we are in a stage where it became frustrating. Basically, there is no alternative to lattice field theory if you want to do real, exact analytic calculation for an arbitrary field theory. Non-perturbative calculation for an arbitrary field theory. There have been attempts to connect string theories to gauge theories and get some information for very specific cases. You might have heard of gauge gravity duality theorems and things like this. But in general, non-perturbative field theory is unsolvable unless you go in Euclidean space and you do lattice calculations. But if you do lattice calculations in Euclidean space, then you only have access to a limited number of observables. Okay, again, this second part of the class was deliberately sloppy because going more into detail would have taken me many lectures, and I cannot do that since this course does not have quantum field theory as a prerequisite. I rather do things that everybody can do. But I found it a good thing for you guys to know what people do in lattice field theory and what is, say, lattice quantum chromodynamics basically refers to. Okay, bye-bye.